Okay, good afternoon, everyone. Welcome to EECS151 251A, Introduction to Digital Design and Integrated Circuit. Today, we're going to start our nice lecture of this semester where we are going to focus on the discussion on the RISC-V data path and control. Likely, this will take roughly 2 lectures, so both today's lecture and also next Tuesday's lecture. All the slides, we put all the slides in today's lecture so that you have basically a single file for you to review. In case you want to actually either review the different instructions or different format, you have a single file to review, but the content will be covered in 2 lectures. So over the past few weeks, we have been covering some of the technology trend, especially the latest generation of 5nm technology. Since we're getting to more microarchitecture, especially instruction set architecture and some of the microarchitecture discussion, this might be a good opportunity to actually introduce or share with you actually one of my favorite books in technology. I guess I still like our textbook better, but this is actually one of my favorite books in thinking about technology and thinking about the dynamics in really managing a fairly complex hardware project. So the book is called Pentium Chronicle. This is actually written by the lead architect of Intel's P6 microarchitecture. This is basically the microarchitecture in the very famous Pentium Pro microprocessors. So this is actually one of the most successful microarchitecture in Intel history, or basically in computer architecture history. It introduced some of the very important topics in computer architecture, especially more modern architecture design, including like register renaming, auto-order execution. Many of the topics it will be covered in CS152 or 252 if you're interested. Besides the technology part, this book is also a really fun read if you're interested in understanding the dynamics of different components in the hardware design, and also just general, the hardware design flow. We talk about the different steps from specification and all the way down to actually hardware design and realization. But actually using this book, it actually gives you a more direct way of thinking about how you need to organize your team, thinking about different components in the design process, and also manage risk. Because this is typically hardware design is actually a fairly complex process, especially as a lead architect. There are a lot of responsibilities in thinking about what you really want to achieve and how you can actually motivate your team to work together towards that goal. And even actually after I graduated, I started working in tech companies for a couple of years, and a lot of the projects that we went through actually reminded me of this book constantly, just both from the different phases of the project, how you actually manage the risk and what things are reasonable, and also how to actually get people working together. We talk about the architecture phase, the design phase, the verification phase. All of those need to actually be lined up in almost a perfect fashion to actually manage a complex hardware design like this. So it's a really fun read since we're getting to more architecture, instruction set architecture, and also microarchitecture. This and next week is actually a good, just in case you have extra time, maybe after this semester, if you're interested in hardware project and also how to manage a fairly complex hardware project, this is a really fun book, and also really, in some way, very honest in describing some of the challenges in building hardware design. And this is roughly more than 20, almost 30 years ago. And it's actually very refreshing to see what kind of technology constraints still relevant today and what kind of discussions are actually not that applied anymore. So a really fun read, a really good book about hardware design and also experience of managing a complex hardware project. Strongly recommended. So with that, let's do a quick, review of, so last lecture, this past Tuesday, we wrap up the state machine discussion, and reiterate the differences between Moore and the MIDI finite state machine and how we can use Verilog to describe those two different flavors of state machine. We also briefly started the discussion about RISC-V, some of the background in how we started, how folks actually started RISC-V at Berkeley more than roughly 10 years ago, and how the different components that's actually being used in the Datapath design. So in this lecture, we'll actually go through the different instruction format in the RISC-V base ISA. So I already mentioned last time, for folks who have taken 61C before, this is more like a refresher, a very compressed refresher. We basically compress roughly 3 weeks of material in 1 week here. And for folks who haven't taken 61C before, or who don't have a lot of RISC-V experience, this is a good opportunity to catch up, to read both the slides and also the RISC-V spec to get yourself more familiar with the ISA, because that will be the instruction set that we'll be implementing in the design project. So back to the RISC-V instruction format, there are 6 different instructions format to encode different instructions. In today's lecture, and also next Tuesday lecture, we'll actually go through the different format, see how they are encoded, how they are actually used to describe different program behaviors, and we'll also conclude that by different control signals that are used to control different data path elements. So let's start with the R-type instruction format. As name suggests, R-type instruction is basically a register-to-register operation. And one thing you will see actually frequently when we talk about instruction format is this 32-bit bit field here with different regions or different parts of the bit vector are encoded for different functionalities. So in all the RISC-V instructions, it always have 32-bit instruction, or here 32-bit or 4-byte is basically a word here. It divided into different fields to encode different information. So we'll start with a register format or R-type format instruction. So all the R-type format follows this instruction encoding, where we start from the LSB. We have the opcode describes the functionality of the operation. And then it's a register-to-register operation. So we'll have 3 register fields, 2 source registers, and 1 destination registers. We also have 2 more, func3 and func7, 2 more fields to actually encode the different functionalities that we like to support. So let's first take a closer look at the R-type instructions. So I mentioned earlier, let's start from the functionalities. So there are really 3 different fields in the R-type instructions to encode the functionality. So first, all the R-type instructions have the same opcode, basically the lower 7-bit starting from the LSB here. So this field with this particular value, that basically means this is an R-type instruction. And then within the R-type instruction, we could also support different register-to-register operations. And those different functionalities are encoded in both func3 and func7 here. We'll see a couple examples to see how we use different bit patterns to represent different functionalities. So first, in terms of functionality, those are encoded in opcode, func3, and the func7 fields for R-type instruction. I mentioned earlier, so R-type instruction is a register-to-register operation. So here specifically, we have 3 registers here. So first, we have 2 source registers, RS1 and RS2, and then we have a destination register, RD here, between bit 7 and bit 11. So here, if you recall last time, we talked about register is one of the most important component of the data path, and all the RISC-V instruction set has, the base instruction set has 32 registers. So here we need RS1, the field RS1, RS2, and RD to specify which one of the 32-bit instruction, which one of the 32 register we'd like to access. So with that, to access 32 different registers, we need 5-bit here to encode the addresses or the index of different registers so that we can access them. So here, 32 registers, so that's why each of the register ID from RS1, RS2, and the destination as 5 bits. So we talk about the opcode for different functionalities and the register specifier here to encode which 2 registers we like to access, read from, and which register we like to write to. So let's see a simple example here. So one of the most basic RISC-V instruction is addition instruction. So it is so in this case we have an addition instruction with 3 registers: X18, X19, and X10. So all the RISC-V encoding will always put destination here first. So the first register here is a destination register, and then we have RS1 and RS2 as 2 source registers. So again, this is very familiar, the bit vector, the bit pattern that we just looked at earlier. So we mentioned that we like to use opcode to specify the operations, and all the register opcode have the same pattern here. And then for addition, we mentioned like func3 and func7 combined are used to specify different functionalities. So here for addition, the particular bit pattern that we are looking for addition are actually all 0. So we have 3-bit 0 here and all 7-bit 0 here. We'll see actually in a minute how we actually can use the combination of the 2 different func fields to encode other R-type instructions. And we mentioned earlier, we need access 3 registers, 2 read, 2 for read, and 1 for write. So the first one is a destination register. So here in this particular instruction, we are writing to X18. So 18 is a destination register. So here we look at our destination field. We encode the value RD18 here, meaning that we are writing to the 18th register here. And then we have 2 source register, RS1 and RS2. Again, we actually write the register index of the different source registers to the corresponding field here. So RS1 here is 19 and RS2 here is 10. So this is actually how we turn an assembly instruction into a bit vector that actually represent this specific instruction patterns. So here we mentioned the addition, the add instruction, which takes 2 operands, 2 registers, RS1, RS2, and write to the register, destination register RD. So what kind of changes that this, after performing this addition actually to our processor or to our finite state machine as a process, to our processor as a finite state machine? In particular, it actually changes two states of our machine. So first, we are writing to a particular register, right? So we're updating a register. So the first change it makes is to actually write to this register. So to the destination register with the sum of the values from RS1 and also the value from RS2. So we are updating this register. And another change it also makes, remember performance program counter is another state in our hardware. So once we actually finish executing the current instruction, we need to update the program counter to the next instruction so that we can actually execute the next instruction. So the second change it makes to the machine state is to update program counter from program counter to program counter +4. So we'll see this in other instructions as well. Besides its actually its own execution, we also need to update the program counter to tell our hardware where to go next. So this is how we encode this add instruction in this particular format, and how it actually changes the machine state, those 2 changes. Let's see how we actually support these functionalities in hardware. So let's take a look at the data path that we need to build for this add instruction. So here, first, we mentioned that to execute an instruction, we need to first read this instruction from our instruction memory. So here, given the current program counter, we actually access the instruction memory, given this particular address, and it returns a current instruction. And this current instruction is an addition. So one thing, after we read the address, after the clock cycle, we get the program counter. You remember the second change we make to the machine state is to actually increment the program counter so that it can point to the next instruction. So with that, we also update our program counter from the current value to +4 using an adder here so that we can update our PC state. So this is the second change that we mentioned earlier. And the first change is to actually update the value of our destination register. So how do we do that? So we read this instruction from our instruction memory. So we see all the different bit fields as listed below here. Now we need to decode instruction to actually see what we really need to do with this instruction. So given this instruction, we actually separate the different instruction field to source register. We need to read two registers, RS1 and RS2. So RS2 here is between bit 20 to 24, and RS1 here is between bit 15 to 19. And then we also need to write to a register here. This is D is for write here. So this is the range between bit 7 and bit 11 here. So after reading those two, after getting the specific region of the bit vector that specify which addresses or which index that we need to access for our register, we can, this is a destination, we can actually read the value out from the register, right? Given this address, remember for read, we just always assume it's a combinational pass. So once you have the read address, you get data from your register, and now you get to your ALU to perform this addition because we're doing an add instruction. And then the result of your addition actually go back to the register because we are actually changing the register state given this, the updated data that we just calculated and also the particular region, the destination register index, we can actually write to our register. So that's how we actually change the state of our register by updating the destination register with the sum of the two source registers. So this is Datapath. Together with Datapath, we also need to consider what kind of control logic that we need to support for this functionality. Well, so far we only have one instruction, so the control logic is not too complex. We'll gradually build up on this Datapath and control logic to see what kind of different operations that we actually need to support. So the first, for this one, the one thing we need to support in terms of control logic, remember the write enable signal that we mentioned last lecture. So when we do read, we can just assume it's combinational. Given address, we get data directly. Given write, we actually need to specify this write enable to actually write to our register here. So here for the write, because we are actually updating our destination register. So during the updating pass, we actually need to specify the write enable signal here. So that's actually how we execute this addition instruction, right? Given this format, looking at it, it's like speaking a language and then decoding this language, right? So once you know how this language is actually organized, you can decode this language for the specific functionality, and then you can build hardware to support this functionality. One more thing we'd like to mention before we actually move on to a different instruction format is how the timing actually, what's the implications of different logic in our timing behaviors for this circuit. So here, if we look at for the current execution, for the current data path, we only have two clocked state element here, the program counter and the register file. So here, let's say this is our clock signal. So our the rising edge transition is here. So during the first, let's start from the left to the right, which is a time here. So during the transition, let's say when the clock first ticked here, that's when we actually go through the program counter here, right? So here we actually update our program counter to the current instruction. Let's see, 1000 actually point to the addition instruction that we just saw earlier. And after we actually sampled the program counter after the clock tick, we can actually do two things, right? One is actually reading the instruction from the instruction memory, and another is to actually calculate the next program counter, the program counter plus the PC plus 4 here, right? So with this, let's say after a certain delay, basically the adder delay here, with our our PC plus 4, basically next PC is updated. And then also after a certain delay here, we actually see the instruction from our instruction memory. And this instruction here, we're just using the assembly here, but this should be basically the 32-bit bit vector that we saw earlier. And then with this add instruction, we can actually separate those into their different fields to actually access our register file. So with that, we take, so RS1, so our X1 is our destination, X2 is our RS1 first source register, X3 is our second source register. So looking at the first source register, which is X2, so we actually read the data from X2 here. Our wire here, this reg RS1 wire is a value of our register, the second register. And similarly, this wire here will get the value of our third register. And then we go through the ALU to actually get the, because we're doing addition, right? So we actually get the sum, register 2 plus register 3. And then after the next, at the clock, at this clock tick, because when we do it right, we actually still at the rising edge of the clock. So at this clock tick, this value is updated into the reg1, our register file, to actually get the updated value. So this is a timing diagram. So far, we're basically still talking about one cycle execution. All this operation can fit in one cycle. Still, there are delays here. We'll talk about the implications on our critical path. And then next week, we'll talk about how to actually use design pipeline processor to make the thing run faster. So with that, so we talked about addition, the register addition earlier. Natural question to ask is how about subtraction here? So here is when we actually see how we can use, in this particular case, use the func7 field. Here we really just flipped one bit. Here, the 30th bit instead of 0 is 1. That becomes basically the subtraction. But everything else is the same. We still read the source registers from the same place and also the destination register from the same place. And the only thing different is the 30th bit of our instruction. So we add another instruction from addition to subtraction, right? So how that would actually change our data path. So now let's look at our data path here. Well, everything else is the same, right? So we are still doing reading data from two source registers and then updating to a destination address register. We talked about our control signal earlier, right? Because we may have some different operations supported in our data path. So we need control signal to actually tell us which operation to do. So here in this example, now in our ALU, instead of just supporting addition, we actually need to support both addition and also subtraction. So in this example, we actually add our ALU select signal so that we can, based on the instruction format, to select whether our ALU is supposed to perform addition or is supposed to perform subtraction. So we only talk about two R-type instructions here, but there are actually other instructions. So take a look at the slide, and if you're interested, also take a look at the ISA. That's ISA specification. That's actually a very good reference throughout the semester to get you more comfortable with a different design. As we mentioned earlier, all of those R-type instructions have the same opcode. And to specify different functionality, we are actually using either func3, those 3-bit for different operation here, or a combination of func7. So here, basically the 30th bit to differentiate either addition and subtraction or logical right shift or arithmetic right shift here. But other things are actually the same, like all the register field for source registers or the destination registers are always the same. It's very important because it has implications in hardware design, and we want to have a very regular pattern to make hardware design easier. So that can.
Quick question about the previous slide.
Mm-hmm. This one?
Is there a reason they chose the second most significant bit for SRA and sub to make them 1? Instead of any other bit?
Mm-hmm. Yeah, that's a really good question, actually. So a lot of the encoding actually has very important implications on hardware. And most of the time, actually, the reason we chose encoding is actually make it easier to decode. So that's actually very important. So specifically in this example, we'll actually see other instructions. So when you actually compare other instructions, it makes more clear. But definitely in this example, we want to actually simplify basically all of those fields will actually differentiate the ALU select signal that we mentioned earlier. So there are the different patterns will actually need different logic to decide the ALU select signal here. And in this example, you definitely don't want to use the first bit because the first bit we'll talk about immediate in the minute, and the first bit actually very important for sign extension. So there are encoding, typically those encodings are actually related to hardware implications and also avoid confusion compared with other instructions. So we'll see actually more examples there in a minute.
I see.
But very important, and you will actually notice that during your design project. Mm-hmm. Very good question, Prashant. Mm-hmm. So as we mentioned earlier, we'll talk about register to register operation. And next we're going to talk about the immediate or I-type instruction. Also very important and very commonly used in hardware, when we actually compile code to hardware. So here, so this is a format that we just saw earlier, the R-type instruction, the three field to specify register, to source registers and destination register, and opcode func3 and func7, different combination to specify different functionality. So here, as the name suggests, we actually want to encode, we actually want to encode immediate here to actually, or constant here to actually add that in our, to support that functionality. It's actually very straightforward. So to actually enforce, as Prashant asked earlier, we like regular instruction format, right? To enforce regularity in our design, we are actually only changing one part. So here, instead of having RS2 and also the func7 field, we're merging those and to have a 12-bit immediate here. So here, the rest of the field RS1, func3, destination, and opcode are actually remain the same. So here we have a 12-bit immediate here. As we mentioned earlier, the first bit is actually used for the sign bit. So this can hold value basically 2 to the 11th. So 12 bits, the first bit is sign bit, so 2 to the 11th, positive and negative 2 to the 11th range. And we'll actually mention in a minute that how the immediate actually need to, because all our registers is actually 32-bit, right? So when we actually load immediate, either as a part of computation or to our registers, we actually need to assign extended to 32-bit before it's actually used. We'll talk about other instructions later to handle if we want to have immediate that is greater than 12-bit. So there are a few I-type instruction as well here. So all the I-type instructions, first, they have the same opcode field here, and they only have destination and source register. So instead of 2 source registers, we only have 1 source register, and another operand, instead of coming from register, another operand is actually coming from immediate that's already encoded in our instruction. And we also use different func3 field to actually represent different functionalities. One thing here, when we talk about shift operation here, so shift operation, again, we are shifting on top of a 32-bit value, right? So at most, you can shift 32-bit because the value itself is only 32-bit. So for the shift instruction, instead of using all the 12-bit here to indicate the shift amount, we actually only use 5-bit here because again, 32-bit register here, 32-bit value here. So shift amount only need 5-bit here to actually specify how much that we want to shift. And one more thing about shift here, very important to notice the differences is also, we already discussed earlier, the arithmetic right shift, arithmetic right shift, or logical right shift. So we actually have 2 instructions here. They have the same func3 field, but the difference is actually similar. If you see the pattern, you see the pattern now similar to the add and subtract. We're using this bit to actually flip the different logical shift and arithmetic shift. So for logical shift, right shift, so left shift is the same, right? So we shift left and we add 0. to the LSB when we actually shift right. So what's the difference between a logical shift and the arithmetic right shift? Any guesses?
Is it the arithmetic shift is when you shift with ones and the logical is when you shift with zeros?
So good guess, you're in the right direction. Why do you think for arithmetic shift, we shift with 1?
It's to keep negative values.
Mm-hmm. But what if the value is actually positive? Do we also shift 1 or we shift 0 here? You're almost right. So absolutely for logic shift, we actually add 0 there, but for arithmetic shift, instead always add 1, we actually do sign extension. Depends on the sign. So you see a negative value, we add 1 and to the left, but if it is actually a positive value, we basically add the sign bit. So it's always, so for arithmetic shift, it's always shift and add the sign bit, versus for logic shift, we basically shift 0. We add 0 to the left. Okay, so those are basically different I format that we can use to handle immediate. Let's take an example to see what this instruction, how this instruction behave. So here we have add immediate instruction here. So instead add, we add I here, represent immediate. So here we mentioned instead of 3 registers, we have 2 registers. Again, the first one is always destination register, so X15. So in this particular example, X15 is our destination register, and we have 1 source register and another operand is an immediate value, immediate here. So in this case, again, this is our I-type instruction format. We have 2 register, 1 destination, 1 source, and immediate here. So to encode this assembly instruction in binary, so here we put destination register, which is 15. So we encode 15 here as our destination register, and source register is 1. So we put 1 here to represent the first register here. And to encode immediate, we actually encode negative 50 here in the immediate field. And it's a negative value. So all the sign bit is 1 here. So this is basically an instruction format and how we translate assembly instruction to this bit vector. Then you will see the pattern here where we talk about instructions, the general format, example of an instruction in that format, and then how to actually design our data path to actually support that instruction. So let's back to our data path. This is the one we have been building so far. So this is our data path that support addition and subtraction here. So what do we need to do? You will also want to extend it to support immediate operation. So recall that for immediate type instruction, instead of reading for the second operand, instead of reading from register, we actually grab the value from the instruction directly and feed it to our ALU here. So in this case, if we look at the data path, what we need to update is basically the operand, the second operand to our ALU. Instead, always from register file, it should also support actually from the instruction directly to our ALU. So to support that, first, remember the mux, the multiplexer that we discussed in the data path element. So here is where we're going to use that. So here we actually add a mux here to select based on different instruction format. We may select either coming from register directly if it's a R-type instruction, always from the register file. But if it's actually an I-type instruction, we actually need to grab the immediate as the second operand. So we'll actually select the second part. So whenever we have a mux, we actually need to have a selection signal to tell our mux how to behave, right? So here, besides the first ALU select signal that we saw earlier, we introduce another selection signal, bselect. Based on the instruction type, you select either the second register or the immediate. So here we talk about, we have the immediate here as a 32-bit value, right? All our operations are 32-bit. But the instructions that we decoded earlier only give us a 12-bit immediate, right? So to support this 32-bit immediate, we also need an immediate generation logic. You will see actually more moving forward because we have different types of immediate need to support. But first, let's just focus on the I-type instruction here. So we talk about the upper 12-bit actually are used as immediate. And let's have an immediate generation logic. We'll talk about how this and the functionality of this logic in a minute. But the goal of this component or the goal of this logic is to actually extend this immediate from a 12-bit value to a 32-bit value so that it can be used in our ALU during the execution stage. So here we also introduce an immediate select signal. So far we only talk about I-type instruction, only one type of immediate. We'll see other type of immediate so that we may also need to have different functionalities here and then use this selection signal to select different functionality. So that's our data path. If we do the execution again, every time when we execute instruction, we need to increment our program counter to get to point to the next instruction. And then once we get the instructions from the instruction memory, in this case, we actually only use, we actually use the value from the upper 12-bit, goes through the immediate generation, extend it to a 32-bit immediate, and set our B select signal to be 1 so that the value of our immediate is actually forwarded to ALU, and then perform our addition between a register value and the immediate. And we still have our destination register, right? So the value, the computed ALU value is actually written back to our register file, right? So we actually only introduce 2 new logic here to support immediate operation in our data path. So a little bit more about the immediate format. So we actually already mentioned earlier, we are actually extending this 12-bit immediate in our instructions. So the top block bit vector here is an instruction format. Again, 32-bit opcode func3, destination register, source register, and for I-type, we have this 12-bit immediate. Right, as Jason mentioned earlier, so for all the signed value, the first bit is actually the sign bit. So the first thing we need to do when we convert this 12-bit value to a 32-bit value, we actually do sign extension here to actually occupy all the upper bit here using the sign bit, and then take the lower 11-bit to as our immediate, starting from the LSB, our immediate value. So this is how we extend from 12-bit to 32-bit, and then the first bit is sign, so we sign extend all the upper our MSBs to make sure we have the same value here. And you may notice that we are actually adding functionality. We'll see this is the first immediate selection. We will actually see other immediate later. And the sign extension or immediate generation here is typically in our critical path. We'll see all the different complexities associated with immediate, especially during the design part. So when you, in the first checkpoint of your project, when you start thinking about your project, always also think about where you like to perform the immediate generation to have a more balanced pipeline here. So with the I format, let's review our data path here, right? So all the blue is what I've seen before, and we mentioned we actually only introduced 2 new blocks here. One is this mux with the B select signal to actually select which value to use for the second operand, and also an immediate generation block to actually, in this case, basically doing sign extension to convert a 12-bit value to a 32-bit value. So for the ALU select, we only talk about the add and the subtract, but we can actually basically having different ALU select signal, we can specify all the different operations that either in I-type arithmetic operation, but also R-type arithmetic operation. So that's our data path so far. So here we mostly talk about immediate I-type instruction for arithmetic operation. In fact, another category of instructions are also I-type. Those are basically load instructions. So what does load instruction do? So load instruction load data from memory and write it to register file, right? So to perform this operation, we need to know which address that we need to use to actually load data from memory. So we need to calculate the address that we use to access memory. We also need to know which register we need to update. We still need a destination register so that we can update our register based on the memory content. So in fact, the load instructions are following the same format as the arithmetic I-type instruction that we just seen earlier. So very similar, we have our opcode, but now we actually need to use to load to specify. We're doing a load operation. Again, we need to update our register, right? We load value from memory to update our register. So we need to specify which is our destination register. And we have this func3 field. We'll talk in a minute. So far we are actually always loading 32-bit or basically 4-byte or a word. We always load 4-byte, which is a word here, but we could use the func3 field to represent different ways that we want to load from memory, either a full word or a half word or a single byte. So that's how we use func3 here to encode that information. And then we need a source register. What does this source register do? The source register, together with the immediate, the 12-bit immediate that we already saw earlier, together using both the source register, we can use the value inside our source register as a base of our memory, and then using the immediate as an offset. So when we actually add our base with immediate, that will be the address we use to access memory. So again, remember the two operations we need to do. First, figure out which address that we need to access from memory. So calculate the address. And then once we load value from memory, we actually need to specify where to store that value. So that will be the destination field here. So again, you see the pattern that we have here. Let's take a look at an instruction here. So let's say we have a load instruction. So here, load word, which is basically loading 4-byte from our memory. So again, we have the first is still the destination register. So we have our destination register, which is 14. So here in the destination register field, we encode 14 here. We want to write to the 14th register. And then we also need to calculate which is the address that we want to access. So to calculate the address, we mentioned earlier, we use a combination of source register and the immediate, the offset. So we use the source register to store the base, where the base address is. So here the source register is L2. So that's basically RS1, this field is 2, because we're using the second register as our base. And then the immediate is actually encoding the offset. The offset of the memory access is 8. So the way we do the address that we want to access the memory is the value stored inside the X2 plus the offset here, 8. So that will be the address that we use to access memory. So once we have this instruction format, we actually know what are the address, which is the address by calculating, by adding the base register value with the offset. We know which address we want to use to access memory. And then we also know which destination register we want to use to store the updated value here. So we finished the instruction format. Let's see how what's the implications of this instruction format in our data path. So again, the blue and the black is basically what we have seen before to support register type instruction or arithmetic immediate type instruction. Now we add a new type of instruction, load, right? So when we do load, we're introducing memory here. So here we introduce our data memory. We mentioned we remember when we talk about the state of our data path, we also have, besides the data register, we also have data memory here. Again, for discussion in this class, we can always assume the read path is basically combinational. So here, when we actually get the address from, so in this case, calculated from our ALU. So once we get the address, we actually, the data memory will respond with the value of the data in that particular address here. And whenever we have memory, we mentioned that we actually need, similar to the register, we have the write enable here to differentiate whether we're doing a memory read or memory write. So here we introduce a new signal here, the memory, a read-write signal to specify whether we're performing a read operation or a write operation. So here we're doing a load, right? Load is a read operation, right? We are reading data from memory to register. So we are performing a read operation. So we specify the operation we're performing is a read, and by getting the data from the memory. So before, the ALU result always directly go back to register. Now we have another alternative source of data, right? Instead of directly from the ALU, it can also come from the memory. So whenever we have actually two sources, and we need to actually dynamically select which one actually go to the next stage, we always introduce multiplexers, MUX here. So here we introduce a new MUX here. We call this write back select. It's a selection signal to select which value is actually propagated to the register, to actually write back to the register here. So whenever we have a MUX, again, we need to introduce a select signal or a control signal to select which entry, which input we actually want to forward. So in this example, let's see how we execute a load instruction. Again, very similar as what we've seen before. We use a program counter to access the instruction memory. And by reading the data, by reading the instruction out of the instruction memory, we actually have the different field that can be used either to access registers or, generate immediate. And for load, again, is an I-type instruction. So I-type instruction has one source, one destination, and one immediate field. So here, well, again, we always need to increment our program counter. So immediate, so we only use a single source register. So we use a source register, first source register to read the value out of RS1. And the second input to our ALU is actually from immediate. This is the same as the arithmetic I-type instruction that we have seen before. And then we perform addition to calculate the address that we actually want to use to access our data memory. So here we have address. We go through our data memory to get our data, right? Specify address, we get our data. And then the second part of the load operation is to update, write this data back to register. Right, so now this data, again, going through our write back select signal, is being written back to our register. So here we actually perform the load operation that largely, actually this part is the same as our I-type, our arithmetic immediate I-type instruction, but adding this memory here, and we introduce two more control signal. One is to specify whether we're doing read or write operation, and another one to specify whether we're writing back using the value from ALU or using the value from memory. You are doing a load operation, we are using the value from the memory to do the write back. So that will be how what's the data path we need to support the load operation. Again, it's still an I-type instruction, just with a different functionality. So there are actually different flavors of load instruction. We are mostly talking about load word, basically always load 32-bit values, but we can actually use, remember the func3 field. We haven't talked about the func3 field much for the load in the context of the load instruction. So for the load instruction, we can actually specify different amount of data that we want to read out of the 32-bit. So for the load word, we want to load the entire word, which is already 32-bit, right? So that's basically the same as the register width. But we could also either load a half word here. So half word here is basically half of the word size. So one word is 32-bit, half of word size is 16-bit, basically 2 bytes. Or we can actually load a single byte here. So it's basically LB. And then we also can load unsigned value instead of signed value. So here we use U to indicate unsigned value here. So again, so to actually specify which part of the bit we want to use. Again, we actually need another mux here, right? Remember, we need to select. We need a mux to actually tell us how to select, right? So we basically need another mux to specify whether we're select the entire word or only a subset of the word. So that's another thing to keep in mind when we think about load operation. We not always want to load the entire word 4 bytes. Sometimes we actually want to load a subset of that.
Professor, quick question.
Of course. Mm-hmm.
So does the memory support this instructions, or do we always load 32 bits from memory and then we do manipulation on it to get like a byte, half word, or like a unsigned?
Mm-hmm. So that part is actually not specified in the ISA. It depends on the implementation. Either you can, if you assume the memory take care of that, and then you basically, the memory already return the specific region of the data, and then you don't need to worry about it, or you actually need to specify how to support that. So in this part, we are actually assuming memory is not taking care of that. The data paths actually need to select the specific region of the data. But that's basically depends on the implementation, yeah, how you support that. But you need to always guarantee that you load the right portion. When you write the value to the register, you load the right portion of the value there. Mm-hmm.
Would it be more costly to load like to do this in memory? For example, like if we are loading a byte from memory, so that means that operation would not be that expensive because we are loading less data from memory. So would that be like a preferred choice over like getting 32 bits from memory and then like basically just getting the input that you want?
Right. It depends on whether you can change the memory, right? So if you are given a memory, then you can actually only access because the output of the memory is always 32-bit, which is one line of the SRAM structure. You can actually not if you cannot specify that in your memory, then you have to take care of that in your data path. But if your memory, you can actually customize your memory to support that, and maybe your memory each bank is already single byte, and then you can actually only read 1 byte instead of the entire 4 bytes. So it depends on the implementation, depends on your memory structure there. Mm-hmm. We'll talk more about the physical, how we actually build memory in hardware and what kind of parameter that you have in the hardware design to support different memory structures. So it actually depends on the memory, what kind of memory you have here. Mm-hmm. And if you have a simplified memory where you only load all the 32-bit, or basically entire word out directly, then data paths need to actually handle which subset to select here. Mm-hmm. Yeah, but from an efficiency point of view, if you can actually customize that memory, it's more efficient to do that. Yeah, because memory operation is always expensive. Mm-hmm. Make sense?
Yeah, because like I was thinking maybe we could like read 4 bytes at a time in parallel. If somehow we could do that, then like doing a load word, which is like doing all of them simultaneously, like there might be some difference if we did like load like 4 load bytes parallelly versus just doing entire load word.
Oh, you're thinking about what if you have 4 instructions of doing load byte versus 1 instruction doing load word directly?
Yeah.
That's a very good question. You can think about it, especially just from, well, most of our discussion is actually, what we talk is actually this part, right? Whether we actually, once we read data out, how we actually specify which region of data that we want to select, right? So if we want to select a subset, we actually need to add another mux here to specify which one to select. But if you're talking about either issuing 4 different load bytes versus issuing 1 load word, that's also related to the rest part of the pipeline, right? Because each of the load byte will be actually a dedicated instruction here. So it's not only just this part how we actually do selection, but also other part of the pipeline. But think about it. That actually can be a very good, maybe a good midterm question to see the difference in executing that in those two fashions. Think about it. Okay, let's move on. So we talk about two types of instructions, register to register operation and also immediate operation. Next, we're going to, so we already talked about load operation, right? So load operation, loading data from memory to register. And then naturally, the next question is, how about store? How we can actually store data from register to memory. Let's talk about what's the encoding for the store instruction here. So again, if we think about store instruction, we talk about load, it still have the destination register, but it only needs one source register. So when it comes to store here, we actually don't need destination register. We're not writing anything to our register here. So we don't need this destination register field, but we may still need actually two source registers, where one of the source register need to actually specify where I want to, again, to calculate the address, which address, where I want to write my data to. So that will be one of the register. And another register, we actually need to specify what data we need to actually to store to memory. So that will be the second register to store the particular data that we need to store to memory. So in the store, for store instruction, again, we still actually need two source registers here. In this particular case, we actually use the first register, RS1, to specify the base of my memory access. And then we still use immediate to represent the offset. And then the value that we are writing to memory, the value we want to write to memory, is actually from RS2, basically the second register here. So in this case, we actually don't need destination register. We only need two source register here, but we also need an immediate here. So to actually store the immediate, you may notice this very weird format where instead of actually have a contiguous immediate region, we actually separate those immediate here, where the upper 7-bit is stored in the same location where we have been storing immediate. That's what we have been seeing before. But the lower 5-bit is actually stored in where we used to. So where do we actually store? Where we actually use those 5-bit for before. So this is where we use for the destination register, right? Because the store instruction, it doesn't actually need destination register. So here we actually use, take advantage of the additional 5-bit here to actually store the offset here directly. So you might be wondering, this is actually a very weird way of actually designing, storing our immediate, right? We're actually splitting that into two parts and they're actually so far apart. So why don't we actually, let's say, just take the RS2 to store the immediate here, but actually moving the RS2 to where we used to store destination. Well, so here, that's again, back to some of the discussion we had in terms of implementation complexity. We actually always want to have fixed place for certain things, so that once the register, once the value is actually read out from our instruction memory, we can immediately decode that to actually do our register access directly. So we want to have fixed places for our register accesses. It's always of higher priority because everything is actually dependent, the values of reading from registers. But versus compared to immediate, so with that, we want to have a fixed format for all our register access. Well, immediate is actually less, compared to register name, less critical. With that, we can afford take a little bit more time to do immediate generation, combining those two fields together while we're doing the register access. We also want to have fixed place for our register, have very simple encoding so that we can get to our register access as fast as possible. So with that, we always have specific encoding for our source and destination register. So again, let's take a look at an example here. So let's do a store instruction here. We mentioned earlier, there are still two instructions for two source registers, one for base, one for the value we want to store, and we have an immediate that's actually used to specify the offset. So in this case, we actually don't have a destination register. So the first one is The first one is actually the second source register, where we specify which the value, which register store the current value that we want to store to memory. So in this case, RS2 is 14, so we encode 14 in the RS2 field, and X2 is RS1, which is used to specify the base address. So it's RS1 is here, specify the second register, and then to specify the offset. The offset here is 8. So instead of storing 8 directly, we actually split 8 into 2 fields. So parts, the lower 5-bit is actually stored in where we used to store the destination register, then the upper 7-bit is stored in the same immediate field that we had before. And with that, we combine, when we combine those two fields together, we get a 12-bit. So in this particular example, the offset is 8. So we specify 8 here in our lower 5-bit of our immediate. So we'll talk about instruction format. We have an example to see how the encoding works. Let's see how that actually changed our data path. So this is a data path that we saw before for load. After the load, we support R-type instruction and I-type instruction for both arithmetic I-type and also load I-type. So for store instruction, we are actually reading a value from register and the store to memory. So in this case, remember the write enable signal we had before to specify whether we want to read or write memory. So here, once we actually read the, remember RS2 was the value that actually specify what value we want to, which register store the value that we want to move to memory. So after we get that value, instead of going through ALU, we actually, the value doesn't need to be recomputed or perform any computation there, right? So that value is actually going directly to our data memory. So this will be the data. So before we only have address to specify which data we want to read from. Now we actually have address and also specify what data we want to write to. And then by setting this memory read and write signal to write, meaning that we actually want to write to our memory. So that specifies the write operation here. So you will actually see what kind of region are actually used for our store operation. So here, the upper left, we're still updating our performance and program counter is the same. And then when we look at the address, it's the same place. We mentioned that we don't want to make this part too complicated. It's the same place to actually execute the instructions. And then the value from our first source register is used as a base to our memory, right? So this will be base, and then the immediate is the offset. So in our ALU, we add the base with the immediate so that we have the address to our data memory. And then the value from register is the value that we want to write to our data memory. And then by specifying we are doing a write operation, we update our memory. So that's basically, again, we are doing incremental change. You will see actually, we already have the memory here for the load. So here, store is basically specify, we can also write to our data memory instead of just doing read. And for write, we need to set the write enable to be 1 so that we can write to our memory. So again, so for load, we talk about load, it has different bit weights, and also for store, we can also use the func3 field to specify which region of the data we want to store, how many bytes we want to store to memory. So far we have talked to a couple of different immediate format, right? So specifically for load and store or for I-type and S-type, there are 2 immediate formats already, right? So the I-type, we actually merge the upper 7-bit with the RS2 to form a 12-bit immediate. But for store S-type, we actually merge upper 7-bit with the destination register to form, again, the same 12-bit immediate field. So you will actually notice, again, we mentioned that, want to mention that the destination, the register field is the same. So that's very important. We want to have fast register access. But at the same time, you will actually notice the majority of the immediate, if we think about the immediate, the 32-bit immediate value, right? So majority of them actually coming from the same place. So first, we still need to do sign extension, right? Because we're converting a 12-bit immediate into a 32-bit immediate. So we always need to do sign extension. And then for the 7-bit, the first bit is sign bit, and then the rest of the 6-bit always being actually assigned to immediate 25 and 30. The only thing actually different from those two fields is actually the lower 5-bit, whether it's actually from this region that's originally used for RS2 or this region that was originally used for destination. So here, whenever we have a choice that we want to make, depends on different instruction, we want to make different choices, then we always need a mux to actually select which, whether if it's I-type instruction, we want to use the upper, the RS2 field for the lower 5-bit, but if it's a store instruction, we want to use the destination 5-bit field for the lower 5-bit. So those are the two immediate that we have seen so far. We'll see actually a little bit more, and things will actually get a little bit messy in terms of how different fields actually work together. But high level principle is we want to enforce as much modularity as we can by having the same places for our destination and for our register operands, and also the same pattern as much as possible, especially for the first sign bit of our immediate. So before we move on, a couple logistic items here. So as you may all know, we are having our midterms in roughly less than 2 weeks. So it will be an in-class midterm on Tuesday, October 6th. So mark your calendar. It will be roughly like an hour and a half. So mark your calendar. And Harrison already sent out the midterm flow. So make sure you go through that. Very important. Just see how how we actually organize both midterm and finals. Harrison and Zhenghan will organize a review session before the midterm. Or I believe there is already a poll going on Piazza. So let them know which slot work for you. We hope to find a slot that works for everyone across the globe. During the review session, we'll cover things that we have discussed so far, and also go through some of the old midterm problems. They might be relevant, they might be not relevant, but it's a good practice for the specific midterm we're doing on October 6th, but overall it's a good practice. It's optional, but it will be recorded, the review session. So the topic for midterm, it will basically up to the RISC-V data path and control, basically this slide deck. We probably won't finish this slide deck today, but so it will be done, basically everything after next Tuesday's lecture, but all the instruction format should already be included in this slide deck. And the pipelining, we'll introduce pipelining next Thursday, but pipelining will not be part of the first midterm. And as we mentioned earlier, we will not have new lab this week. So use this week to catch up the old labs and also review the topics and prepare for the midterm. And we are also having our fourth homework out this week. So we'll post the homework, the fourth homework shortly after the lecture. It will be focused on the RISC-V ISAs, instruction format, and also data paths. So very useful for students either have taken 61C before, use that to refresh yourself. For students who don't have a lot of experience with RISC-V before, that's also an enforcing function to get yourself more familiar with the content. And part of the midterm, the first part of the midterm, Harrison set up a short problem, well, short really paragraph to actually go through the midterm setup. So definitely go through that, go through like what kind of, like set up your Zoom, submit your Zoom ID so that we know which link, and also go through one problem so that you can actually test your recording, and also submitting your recording, making sure things all work right. So homework 4 will be very useful for both the topic and also for the midterm practice. So take a look at that, and hopefully that will be helpful for the midterm. So any questions, comments on midterm, lab, and homework this and next week? Okay, so if you have any questions, let us know. Definitely use this week to catch up the lab and also review the topic, and we'll hopefully we can use the midterm as an opportunity to actually help you to refresh all the different content that we have covered so far. So next, we're going to talk about the B type. We talked about already 3 type, right? Register, immediate format for both arithmetic, immediate, and also load instructions. And then after load, we talk about store, the S format, how we use stored, how we actually specify the store instructions. And next, we're going to get to how we actually change the execution of our program. So we're going to get to the branch format. What are the branch instructions, how the branch instructions are encoded in RISC-V. So that's what we call B format, is basically conditional branches. And you will see the format actually pretty consistently. Like for example, an example of branch format is this BEQ branch if equal instruction here. So we read the value of two registers, and if they are equal, we actually branch to the specified label instruction. If not, we continue the execution. So this is actually similar to the store in the sense it reads the values, reads from 2 registers, but actually not updating any register. It changed the program counter. We'll talk about it in a minute. So it definitely changed the state of our machine, but it doesn't actually write to register. Now we get to the encoding question, right? So to specify this functionality in our instruction format, in our bit vector, how we can actually encode that information. So before we get there, we talk about branch, where branch actually need to jump to different places of our program. We actually need to take a look at what are the granularities that we're jumping around for the branch instructions. So far, most of our discussions are talking about 4-byte or 32-bit word before, but branch is a special case where we're instead of 4-byte, we're actually navigating around 16-bit or 2-byte field here. The reason for that is that also, like all the instructions that we cover, especially in this class, is actually 32-bit. Everything is actually 32-bit. Some extensions of RISC-V, specifically the E extension, the embedded extension, they do support even more compressed instruction formats. Specifically, instead of using 32-bit to encode instruction, they can actually support 16-bit to encode the instruction. We'll not get into that in this class. It's basically another instruction extension that support more compressed format. It is still useful, right? So if you think about, especially in, like as the name suggests, it's an embedded scenario. In the embedded scenario, we actually really care the program size, right? We want to minimize the size of our program as much as possible. So with that, having an efficient encoding so that the program doesn't actually take a lot of space is very important. So that's why for some of the extension, we do support more compressed formats, specifically 16-bit or 2-byte to represent an instruction. So with that, RISC-V in general, actually to make it actually flexible and compatible across different instruction format and also across different extensions, we actually always, when we talk about branch instructions or jump instruction, we are actually changing the execution flow. We always talk about offset, branch offset in 2 bytes, by 2 bytes or 16-bit. So instead of branching offset by 4 bytes, we actually always offset by 2 bytes. So that for this embedded extension, they can also jump to their specific location here. With that, so also our program is actually 4-byte. So if we actually do a 4-byte, we could actually potentially have more, we only need to specify word address, right? If everything is 4-byte. But now if everything is 2 bytes or half word byte, we actually need to specify half word address, meaning that we actually miss basically half of the potential target that we could have specified if we only need to specify 4-byte offset compared to 2-byte offset that we have now. So if you think about the immediate field that we've seen before, we have a 12-bit immediate field, and the first bit is always used to specify to specify the sign bit, right? So we have 11 bit to specify the 11 bit to actually specify the immediate. So if we are actually doing 4-byte offset or 4-byte delta here, we could actually use 2 to the 11 to specify the branch range. But instead of using 4-byte, we're actually doing 2-byte or half-word branch distance. So we can actually only specify 2 to the 10. We basically waste 1 bit there because we only do half-byte instead of 2-byte here. 2 to the 10 4-byte range, 4-byte instructions, because we miss actually we have to support the 2-byte format here. So what's the implications in our instruction format here? So let's talk about instruction format first, and we'll use an example to see what's the implications of doing 2-byte offset instead of 4-byte offset. So again, this one looks really busy, right? So we talked about the different instruction format before. This one actually looks particularly busy with all the different factors coming in. But still, let's see like those that we're very familiar with. So we still have opcodes. Still, the lower 7-bit is our opcode. And then we also have our func3 field to specify different sub-functions that we like to support. And then we still have our 2 source register. Remember, for the branch instruction, we also compare our 2 source registers. So we still have our 2 source register. What makes this a little bit messy is actually how we store the immediate here. So we are still storing using 12-bit to actually store the immediate here. There are some patterns here in the sense that we still use the first bit here to represent the MSB, the sign bit. So that part is actually the same place. But compared to the store immediate that we saw earlier, where we actually use the 5-bit actually to store the lower 5-bit here in the destination register field, and then store the rest in the upper bit. Here we actually store the immediate, because we talk about the byte half-word addressable, right? So memory is actually byte addressable. So we actually specify the byte address. So now we actually need to do half-word addressable in the sense we actually specify every 2-byte. So with that, we actually don't need to specify the last bit to actually specify which byte we like to access, because everything is actually indexed by half-byte. So with that, we actually don't need to specify the LSB or the LSB, the byte address, because it's always 0. Everything is actually lined up in a 2-byte fashion. So now we actually basically have 1-bit actual space here to keep everything consistent so that we don't need to change a lot of things. So instead of actually moving, let's say the 5th bit, which was actually used to store here to here so that we can have a contiguous region, we actually keep everything the same by having, but since we can actually have one more bit, because we're not doing byte addressable, we're doing half-word addressable, we're actually moving the 11th bit to actually the 7th bit where we used to actually store the 0 bit before. Let's use an example. It may seem a little bit confusing, just seeing how this different bit field actually gets scrambled together. Let's use an example here. So recall our branch equal instruction here with 2 registers and an offset here. So we have 2 registers. We compare the value of the 2 registers, X10 and X19. So here we use RS1 and RS2 to specify 19 and a 10. So we have those 2 fields here. And now we actually need to specify the offset, which is 16. The offset is actually 16 bytes. So here, let's say specify this with 16 bytes using the 13-bit immediate here. So this is 16. In a byte addressable fashion, we actually need to encode the 16 in our instruction. So first, for branch, instead of byte addressable, we're actually doing half-word addressable. With that, we actually don't need the last bit because every is 0, and because every instructions, we are actually always doing half-word addressable. So we don't need to store those zeros. So those 13 immediate become actually 12-bit by discarding the last bit here. And then to store this into our instruction format, there are some common ones, right? So the, let's say the lower 4-bit is actually still the same place where we used to store the bit 5 to bit 5 and 0 here. We just discard the lower bit. This bit is actually discarded. And then the upper bit is the same. This is the same as our store immediate format, where we actually store this 6-bit to actually the upper 6-bit field, except the sign bit. So here is where we store the 6-bit. And then, we still have the sign bit, which is actually stored here. But one thing different here, because we actually have one more bit free space. We don't need to store this lower bit anymore, the LSB, because it's always 0. We actually don't need to do byte addressable. We just do half a word addressable. We can actually store one more bit. This bit is actually very important. It's basically double our branch, our instruction range. So in this case, we actually want to keep this word so that we can double our instruction range and then store this word here so that we can use almost the same format, but with minimal change. But actually get to a bigger range by storing one more bit. So just a quick summary. We'll pick it up from here next time, but look at all the 3 immediate that we have seen so far. IType instruction, store instruction, and also branch instruction. They all need immediate, but they store immediate in slightly different way. Take a look at the different format, review it, get familiar with it. We'll pick this up again next week. Well, good to see you all. Take care. Hope you all have a good weekend, and let us know if there's we don't have new lab this week, but we will do our first midterm in less than 2 weeks. So take care, enjoy your weekend, and we'll see you next week. Bye. And I'll be around for a couple more minutes if you have any questions. Let me stop the recording first.